So let's read off some things. So there's a graph of a function. What would you say is the largest value that this function takes? 5. Why 5?
It's the greatest y value. The range.
Yeah, it's the biggest y value in the range. And that makes sense. If you want the maximum value, that's like an output thing. It wants the biggest output. Outputs are y values. So because of that point, you see a maximum of f of x equals 5. What if you wanted more than that? Like, that tells you like what the best you can do if you want, if this were like profit you could do by making some decision parameterized by x. Then the maximum profit is 5, so you should do whatever choice gives you that maximum profit. What's the input that gives you that maximum profit?
-6.
-6. Is it -6 or -5? I think it's 5. It's the one that's farthest to the left. Cool. So, and that's because this point at -5, 5 is the highest up point on the graph. What would you say the minimum value of this function is? Yeah. -4. Cool. Why -4? Yeah, it's this lowest point, which has a y value of -4. So the minimum value this thing takes is a minimum value of f of x equals -4. What's the input that produces that minimum? Two. Cool. Nice. So, if you want to maximize or minimize a function over some domain, then one thing you might talk about is global max and global min. An input C is called a global maximizer for a function f if the output you get by plugging in that C is at least as big as every other output you could possibly get. That makes sense why that should be? A thing is a maximizer if it's an input that gives you the maximum possible output value. Minimizer. An input C is called a global minimizer for a function if something an awful lot like what I just wrote in red happens. And I don't know, how would you want to change that to get the idea of what a minimum should be? Just flip that inequality? You want an output value that's now less than or equal to every other output value? Seems sensible? All right, so let's talk about local behavior. And I had like a little piece of plastic that seems sensible for a bit of shtick here. Okay, that's frustrating. Oh, there it is. Okay. I'm going to zoom in some. Any questions right now? All right. Let me zoom in as close as I can. There used to be a dochem in here that had like up to 100x zoom, so I could do this shtick really well. But right now we'll settle for this. So let's suppose that you only saw the piece of the graph inside of that little O-ring. If that were the case, the point corresponding to that blue dot, would you say that corresponds to a maximum value for this function? What about a minimum? Yeah. So this point, I would call this point something that is neither a local max nor a local min. And let's see if there are any others. So let's zoom in on some other point, say that one. If you were to only see that much of this function, would you say that that looks like the minimum value? Yeah. So that means that an input of, that's -3. X equals -3 gives a local minimum value. I wrote X equals -3 in the right line. In fact, maybe the zoom in isn't even that important. There, you can see both. And let's just keep on going. You continue just viewing a little bit of the function at a time. Those points, do they look like they achieve a maximum? Keep on going. Do you see a maximum now? Yeah. So what's an input that produces a local maximum? If you keep on going, are there any other inputs that produce a local max or local min that you see? Yeah, what do you see? X equals 2, is that what you flashed at me? All right. Yeah, let's zoom in on X equals 2. Yeah, that's certainly an output value that's less than or equal to all of the other nearby output values. All right, and let's move a little bit farther this way, and let's come up to, say, this point inside of that little red arc. Would you say that that output value is less than or equal to every other nearby output value? Yeah, because I said or equal to, right? Would you also say that it's bigger than or equal to every other nearby output value? I would say that all of the inputs in that interval produce local maxes and local mins. Let's see, I guess that would be 6, 7, 8. Also, everything between 6 and 8. Everything between 6 and 8 exclusive produces a local minimum. And let's just, you'll notice that there, I used different brackets at the endpoints there. Let's see if that makes sense. Let's check X equals 6. Let's suppose you only saw that much. The blue dot at X equals 6, is that Y value at least as big as every other nearby Y value? Is it also at most as big as every other nearby Y value? I mean, it's not, right? Because there are these Y values too. So that's why I excluded 6 there and included it there. So here's, I don't know, I'll stop there. Are there any other inputs that produce either local maxes or local mins that you see? Yeah.
Would X -5 also be a local, considered a local?
Ooh, that's exactly the thing to ask about. And that's definitely like, it's literally an edge case, and it's like a weird edge case in the definition. Because of the way that I'll write the definition in a moment, endpoints will never count. So I'll put this comment right here, and then we'll discuss why endpoints don't count in a moment. So I'll write down a definition now of what it means to be a local maximizer. An input, C, is called a local maximizer for a function f if f of C is bigger than or equal to f of x for all x values close to C. Oh, God damn it, Chris. So a function is a local maximizer if the output corresponding to that x value is at least as big as all of the y values corresponding to x values that are nearby. And let's maybe just start with one of the ones that we actually counted as a local max. So we said x equals 0 is a local max. if I only want to look at x values inside of that really little red interval, pink interval? Does that look pink or red? Pink. Okay, let's call it magenta. Interval. Would you say all the y values corresponding to those nearby x values are less than or equal to this y value? Yeah, that's good. Let's check x equals 5 and see if it should count. So there's x equals 5. There's a little interval around x equals 5. And maybe for emphasis, I'll focus on the ones, oh, that highlighting didn't work at all. Focus on the ones to the left of x equals negative 5. It's like negative 5.01. Is negative 5.01 in the domain of this function? So can I even compute f of negative 5.01? Oh, but negative 5.01 is like really close to negative 5. So you can't even check this inequality if you're at an endpoint. So that's why I would exclude endpoints from consideration. And maybe just to tie back to notions from calculus, local extrema there are tools from calculus that are very well equipped to finding those things where places where tons around. And then you just also have to check endpoints if you want to find global maximizers. But that's again getting caught into a segue that's much more important. How many people are planning on taking Calc 1 next semester? Yeah, that'll be a really important point about a semester from now. Oh, minimizer. How would you want to change this if you wanted to get a local minimizer instead? Yeah, again, just flip the inequality. Cool. All right, so in order to compare what we just did with the idea of taunting points, I'm going to flip back to the example on the previous page of x cubed minus 4x. So there's x cubed minus 4x. What would you say the maximum value this function takes is about it? That's the input that produces the maximum. Anyway, I will ask more questions that trip up exactly that point. I'm asking for the input or the output value. Oh, wait, I don't want to zoom in. So that's a place that produces a maximum. It's also a local maximum. But it's also another thing. It's a taunting point. So here's a thing worth remarking. This is just this takeaway. Taunting points produce local extrema. And hopefully that makes a lot of sense. If you increase until you make it to that point and then you start decreasing, then that's a maximum. It's only a local maximum because you don't know what happens far away. Groovy. That feel pretty good? So there's some notions that, mess around with the webwalk, see if the things in the webwalk make sense. There's an extra credit immediately involving the idea of rates of change. Take a look at it if you want to. So the thing I want to do with the remaining 20 minutes is I want to start building a pool of what I'll call elementary functions. So these will be functions that you should just always have in your pocket as things whose graphs you know, that you know some facts about. And one of them you already have. What's the graph of y equals x look like? Yeah, it's a diagonal line. Let's record some things about that line. Where is its intercept? The origin. And notice I didn't say x-intercept or y-intercept because I didn't need to. What's its slope? 1. So the line y equals x. And it's exactly what you described. It's like a diagonal line. But maybe more precisely, it's a line whose slope is exactly 1 and goes through the origin. There's the line y equals x. Let's get an idea of y equals x cubed. And maybe you already know what the graph of y equals x cubed will look like, but Let's get it by plugging in some points. What's 0 squared? 0. So 0, 0 should be on the graph. What's 1 squared? 1. So 1, 1 should be on the graph. What about negative 1 squared? Also 1. Doesn't matter if you have a negative if you're squaring it anyway. What's 2 squared? 4. So 2, 4 should be on the graph. I think that's enough to get an idea of what the graph looks like. It looks like it keeps getting steeper as the x values grow. Feel pretty good? And that was like a fairly shaky idea of graphing. Like I checked 4 points and then extrapolated. Let's just compare that with a computer graph. Y equals x squared. Home. That look about like what we drew? All right. So one graph you should just always have in your head is something you know is what does the graph of y equals x squared look like? It looks something like that. That shape is generically called a parabola. The word parabola really has like a precise meaning. A parabola is parameterized by a straight line and a point. It's all of the points that are the same distance from the straight line as they are to the point. It turns out that y equals x squared satisfies that with an appropriate choice of point and line. Cool. Let's carry on. Y equals x cubed. Let's play the same game. Let's see what the graph of that looks like. And again, we could plug in some points. And if we do, we'll get a shape somewhat like that. I guess if you want to describe it in words, I don't know. How would you want to describe this in words? I don't know, maybe it looks vaguely like a parabola, except at the origin it switches from upward opening to downward opening. I don't know, that's not a great description either. You can draw a picture. It definitely goes through 0, 0, 1, 1, and negative 1, negative 1. It looks vaguely parabola-y if you only look to that side. It looks vaguely parabola-y if you only look to that side. Let's also get x to the 4th. How would you describe that?
Stretched a little bit.
Yeah, it looks kind of like x squared, but kind of stretched a little bit. Sure. In fact, let's compare it to x squared and see that stretching. So it certainly looks for like x values that are kind of big. The thing to the 4th power is like vertically stretched by a lot. And it looks like close to the origin, maybe it's even flattened. So it gets flattened close to the origin and stretched far away from the origin. But all of that is information that a picture drawn by me isn't going to be able to capture anyway. X to the 6th, do you think that'll look kind of like that again? X to the 8th? In fact, any even power of x will look vaguely like that. Any odd power of x will look vaguely like x cubed. Let's answer some questions just looking at these graphs now. Are these functions even or odd? These functions in the leftmost column, even or odd? Odd. In fact, that's why we call odd functions odd, because odd power functions are odd functions. Even power functions. Even. And maybe just in order to make sure that everything is making sense, what does it mean for a function to be even? So an even function is a function that doesn't care if you put a negative sign inside the parentheses. Do those functions care if you plug in a negative for the x value? No. Also, graphically, like it's given by flipping over the y-axis, and you get the same graph. If you want to flip these over the y-axis, would you get the same thing back? Awesome. Odd. What does it mean for a function to be odd? Like maybe something like that.
When f of the negative x is equal to negative f of x.
Yeah. So an odd function is a function where you can like pull a negative sign out of the parentheses. And let's just check that. Can you pull that negative sign out of those parentheses? Yeah. Cool. Intercepts. Where are the intercepts of these functions? Yeah. 0, 0. Nice. Where are these functions decreasing fast? Where are the odd power functions decreasing? Yeah. Are you answering that for the odd power functions? Ooh, let's check. So I hear a negative infinity to 0. And let's just see. Here's an x value, x1 less than x2. So for a function to be decreasing, the y values should switch in order. Would you say f of x1 is less than f of x2 or f of x1 is bigger than? Less than. So in fact, this is still increasing. Are odd power functions ever decreasing? Nope. So in fact, so if odd power functions are never decreasing, where are they increasing? Everywhere. All of our. So I guess different ways of writing that are maybe blackboard bold R for all the real numbers, negative infinity to infinity, and maybe the most colloquial way, everywhere. Yeah.
Can you explain the test that you did again with the x1, x2?
Yeah. So decreasing means that if you have x1 less than x2, this should go to f of x1 bigger than f of x2. So let's put that in just words. If the inputs are in some order, then the outputs are in the reverse order. And let's just see if that happened. So I had x1 coming before x2. Here I have f of x1. There I have f of x2. Would you say f of x1 comes before f of x2 or after? I guess which way would you put the inequality? Which one is smaller than? F of x1, just because it's lower down? So the inputs are in an order, x1 is smaller than x2. The outputs are in the exact same order. So those two inputs thought it was increasing. And what it means to be increasing is that that should happen for every pair of inputs. Neato. Same thing for the even power functions. Zoom out a little bit. Where are the even power functions decreasing? Yeah. Yeah, what you said before. This time from negative infinity to 0. And maybe we'll check colloquially first. Would you say that the graph is generally going down as the x values go up right there? Yeah, that's what it means to be decreasing.
So we would count
Yeah, so let's check using the super technical definition. The this one. If one input is less than the next input, then the outputs are in the opposite order. So let's test that. So let's test at 0, which is the biggest thing in the interval. Give me something less than 0. -1. I need to know if f of -1 is less than, no, bigger than f of 0. The inequality, I think it should go in the opposite direction. If f of x, well, right now we're looking at x to the 4th. So that's -1 to the 4th. Is that bigger than 0 to the 4th? And let's just check that. What's -1 to the 4th? What's 0 to the 4th? Is 1 bigger than 0? Yeah, that's why I would want to include the endpoint. If you're using a definition that comes from calculus, where you actually compute the slope, you might want to exclude. But we're not using calculus-driven definition right now because we're not taking a calculus class. And there really is this subtlety about whether the endpoint should be included or excluded. And it's a subtlety that I don't want to worry that much about. If on some homework problem, an open-ended thing, you indicate that a function is increasing on some interval and you exclude the endpoints when I would include them, that's not going to make me very upset. Because there are different definitions you can see in different places where maybe they would be excluded. The one thing that will be picky is WebWalk, and that's because it's a computer and those are picky by nature. Neato. So decreasing from -infinity to 0. So I guess it should be increasing the rest of the time. And again, for the same reason, I would want to include 0. Ooh. So there's the first of a pile of elementary functions that I just want to keep in mind. I've got 8 minutes. Let's build another family of elementary functions. And let's start with the square root function. Let's try to graph y equals the square root of x, and maybe you already know what the graph should look like. You can graph it by plugging in some inputs, but I think I want to graph it by thinking about the squaring function first. So if you were to start with y equals the square root of x, what would you get if you solved that for x? Yeah, say it louder there.
Y squared.
Yeah. This would become x equals y squared. And that should look really similar to what's at the top of the page. At the top of the page, we see y equals x squared. If you want x equals y squared, well, that just switches the x's and y's. So this graph, if we just want x equals y squared, will look the same as y equals x squared, but flipped over, the x and y values will be swapped. Would you say that thing I just graphed is a function? No, why not? Fails the vertical line test. But the square root function is a function, right? So in order to deal with this subtlety, let's ask this. Is the square root allowed to ever be negative? And y is the square root, so I'll add this. And y is bigger than or equal to 0. So if you want y equals the square root of x, just throw out all the negative y values. You require that y is bigger than or equal to 0. There's y equals the square root of x. That feel pretty okay? Could we do something similar to get the cube root function? Let's do something similar to get the cube root function. If you want y equals x cubed, well then you can transform y equals, cube root of x to x equals y cubed. And again, oh hey, that looks exactly like something that's graphed on the previous page, except that it's x is a function of y instead of y is a function of x. So let's just recall, y equals x cubed. Looks something like that. Let's take that, flip the x's and y's, there's the graph of x equals y cubed. And now I'll ask the same question. Does that pass the vertical line test? Is it the graph of a function? Oh, cool. So that might just be the cube root function. To do a sanity check, let's just ask, is the cube root of a thing allowed to be negative some of the time? Yeah, like what's the cube root of negative 8? Negative 2, I think, because 2 cubed is negative 8. Yeah, it's allowed to be negative. So this is also the graph of the cube root of x. In general, I think I'm going to blow by just a little bit. If you have anything that looks like an even number, even through root of x, the graphs will all look vaguely similar. So the square root of x, the fourth root of x, the sixth root of x, all of those graphs will look vaguely like that. Whenever you see an odd root of x, they'll all look basically like the cube root. All of the graphs will look something like this. So, cube root of x, fifth root of x, seventh root of x, and hopefully that's not a surprise either. Let's answer some questions using these graphs. So, let's do even roots to the right, odd roots to the left. Let's answer some questions. Even, odd, neither, or both. If you were to see this graph, would you call that an even function? Folks for yes? Folks for no? Well, let's do a quick test. So how do you test graphically if a function is even? Symmetric over the y-axis. If I take a point on this graph and I flip it over the y-axis, do I get a point that's still on the graph? So I'll ask again, is it even? Folks for yes? Folks for no? Cool, yeah, it's not even. It has the wrong domain to be even. If a function is even, it has to have symmetric domain. Is it odd? Folks who want to say it's odd? Cool, for the same reason. Take this, flip it over the origin. Oh, that point is also not on the graph. Even root functions are neither even nor odd. Odd root functions. So take a look at that graph. Would you call that even? Folks for yes? Would you call it odd? Folks for yes? Yeah, great, it's odd. Take a point on this graph, flip it over the origin. Yeah, that looks plausible. Where are the intercepts of these things? Let's take a look. Where does that thing cross an axis? At the origin. What about odd power functions? Where are their intercepts? Same. And let's see. I have 2 minutes by the official clock. Where are these things decreasing? And again, we'll take a look. Where is that thing decreasing? Where is that thing decreasing? So none of these things are not decreasing anymore. You, I think, answered the next question vertically instead of horizontally, which is maybe a better way that I should have organized this. Where are they increasing? Where is that thing increasing? Say it. You just said the right answer to this question. Where are even root functions increasing? From 0 to infinity. And right, like maybe you would want to say they're always increasing, but are all numbers in the domain? No, so it can only be increasing on its domain. Where are the odd functions increasing? Well, from negative infinity to infinity, and maybe we'll close with just a reminder that we have one other elementary function that we just know. We know the graph of the absolute value. So, what will we start doing next time? We'll start using these elementary functions, and we'll start building some moves we can do to sketch graphs of new functions. If you know what the graph of y equals absolute x looks like,
then you can finally graph y equals 5 times the absolute value of 3 minus x plus 7. Cool. All right. So, the previous class, I wish you a happy solstice equinox over the weekend, but this weekend is not the equinox. So do not have a happy equinox this weekend. It's next weekend.